Hello friends, welcome to engineering tutorial. Today we are going to discuss about the basic concept of semiconductor physics. Now these are some of the introductory and fundamental concepts related to semiconductors, which are going to form the basis or the foundation of our study of electronics engineering. So here is a list of things that we are going to cover in today's video. First of all, we are going to discuss about the introductory or the definition of semiconductors, basic information about semiconductors, basic properties, bond formation. Then we are going to study about the classification of semiconductors in on the basis of various properties. Then we are going to study about the bond formation and some introductory concepts about the various types of semiconductors. So let's get started. So what is a semiconductor? Obviously, the name suggests that is half of that of a conductor. Well, a semiconductor is a substance which has its resistivity lying in between that of conductors and insulators. We all know resistivity is the net opposition offered by a material to the flow of current through it. So in simple terms, a semiconductor has its resistivity more than that of a pure conductor, which means that offers more opposition to flow of current as compared to that of a conductor, but it offers less opposition, or it has less resistance as compared to that of an insulator. So it lies in between a conductor and an insulator, with both the conductor and the insulator on the two extreme points. Now the resistivity of a semiconductor lies in between 10 to the power minus 4 to 0.5 ohm meter. So the ohm meter is the unit of resistivity, we all know that. So some basic examples of semiconductor materials are silicon, germanium, selenium, and many more. Materials are also there, such as gallium, arsenic, many more. So these are the most commonly used semiconductors. That's why I've mentioned them. Silicon and germanium especially, they are the two most commonly used semiconductors. So let's just get to know some of the basic properties of semiconductors. Now, as I mentioned in the earlier introductory part about semiconductors, that the resistivity of a semiconductor is less than that of an insulator but more than that of a conductor. So another interesting property about semiconductors is that they have negative temperature coefficient of resistance, which means that their resistance is inversely proportional to the surrounding temperature. As the surrounding temperature increases, the resistance of the semiconductors decreases, and as the surrounding temperature decreases, the resistance of the semiconductor increases. So it follows an inverse relationship between the semiconductor internal resistance and the surrounding temperature. The third interesting property about semiconductors is that they have crystalline structure. Their atomic structure is crystalline in nature, which means that the atoms in the semiconductors are arranged in a well defined or ordered way. A proper design is there, a proper well defined way the atoms of the semiconductors are arranged in a proper way. So that's property number 3, that is, they have a crystalline atomic structure. Now next, the bond formation in semiconductors. Now we all know that both silicon and germanium are the two most commonly used semiconductors, and both silicon and germanium in their electronic configuration have 4 electrons in their outer band or valence band. So here those 4 valence electrons are taken into consideration as they are involved in the formation of covalent bonds. Here we have taken germanium, the bond formation of germanium semiconductor atom. So as you see here, each germanium atom contributes one electron to its neighboring germanium atom. This germanium atom has contributed 1 electron to this germanium atom has contributed 1 electron to form a single covalent bond. Similarly, this germanium atom has contributed 1 electron, this germanium atom has contributed 1 electron to form another covalent bond. So one covalent bond is formed by the contribution of 1 electron each from the adjacent or neighboring semiconductor germanium atoms. In this way, multiple covalent bonds are formed, and a semiconductor material is constituted by the formation of these multiple covalent bonds consisting of 2 electrons each contributed by 2 adjacent or neighboring germanium atoms or semiconductor atoms. Silicon also has a same bond formation structure, as it has 4 electrons in its outer band or valence band, so it also follows the same bond formation pattern. So next we are going to study about the classification of semiconductors. Now here we have classified the semiconductors on the basis of 2 criteria, on the basis of 2 properties: composition and doping level. Now on the basis of composition, the semiconductors are of 2 types: simple or elemental semiconductors and compound semiconductors. Now simple or elemental semiconductors are those which are formed from a single element, a single entity. Example: silicon, germanium, selenium, gallium, arsenic, etc. Whereas compound semiconductors are formed from 2 or more semiconductor materials. They are formed from 2 or more. It can be 2, it can be 3. So they are formed from 2 or more materials. Next is doping level. On the basis of doping level, the semiconductors are classified into 2 categories: intrinsic and extrinsic. We are going to discuss about these classifications in the later ones. So let's first discuss about the simple or elemental semiconductors. Now I have taken here silicon and germanium for discussion, as they are the most commonly used elemental semiconductors. So as I said earlier, simple semiconductors are those which are formed from a single element. Silicon is a single element, germanium is a single element, so they are simple semiconductors. They are composed of one and one element only. So next is compound semiconductors. Now the compound semiconductors are those which are formed from two or more materials or two or more semiconductor materials. That's why they are called as compound semiconductors. Example of these kind of semiconductors are gallium arsenide, gallium nitride, indium phosphide. Now these are made of two semiconductor materials. Now there are also compound semiconductors made from three elements. For example, aluminium gallium nitride, indium gallium nitride, etc. So these are only to name a few. There are many like these, many compound semiconductors like this. So now the next classification is intrinsic and extrinsic semiconductors. Now an intrinsic semiconductor is one which is in absolute pure state, or the semiconductors in their pure state or absolute state with no impurity added to them is called as an intrinsic semiconductor. Now a question might be popping up in your head that why impurity are needed to be added to semiconductors. Well, it has been found that when certain impurity or certain external material is added to an intrinsic or pure semiconductor, its conductivity increases many times. So this process of addition of external impurity atom to a pure or intrinsic semiconductor to increase its conductivity is called as doping. So the semiconductors which are formed by impurity addition or by the doping process are called as extrinsic semiconductors. These semiconductors have increased conductivity levels because of the added impurity and are mostly used in various applications. So next there is a classification of the extrinsic semiconductors. Now the extrinsic semiconductors are classified into two categories, N-type and P-type semiconductors. Now let's get to know what these N-type and P-type semiconductors are. Now what is an N-type semiconductor? So an intrinsic semiconductor which is doped with a pentavalent impurity is called as a N-type semiconductor. So what is a pentavalent impurity? So a pentavalent impurity means it has 5 electrons in its outer or valence band. The outer band or valence band consists of 5 electrons. Now typical examples of pentavalent impurities are arsenic with atomic number 33 and antimony with atomic number 51. These are the examples of pentavalent impurity. So let's understand how this formation of bonds takes place in the N-type semiconductor with pentavalent impurity addition. Let me magnify this image for you. So here, this is the arsenic pentavalent impurity atom which is added to an intrinsic germanium semiconductor. So each arsenic impurity atom positions itself in between 4 neighboring germanium atoms. As we know, the arsenic impurity atom has 5 electrons in its valence band. Now out of these 5 electrons, it contributes 4 of its electrons to form covalent bonds with 4 neighboring germanium atoms. Okay, it has contributed one electron to form covalent bond with 4 neighboring germanium atoms, with the neighboring germanium atoms contributing 1 electron each from their valence band. So in this way 4 covalent bonds are formed between the arsenic impurity atom and the neighboring 4 germanium atoms. Now it has exhausted 4 of its valence electrons. Now 1 electron is left behind, 1 valence electron is left behind, which does not participate in the bond formation or the covalent bond formation process. Now this electron, which excess electron, goes to the conduction band of the semiconductor and is responsible for increase in the conductivity of the semiconductor. So this impurity arsenic, as it donates 1 electron, which helps in increasing the conductivity of the semiconductor, it is called as a donor impurity. So, and the majority charge carriers in n-type semiconductor are electrons. Now let me tell you why they are called as n-type semiconductors. As electrons are the majority charge carriers, which are negative charge, that's why they are called as n-type, negative type semiconductor. So this one is the bond formation in n-type semiconductors. Next we are going to discuss about p-type semiconductors. Now an intrinsic semiconductor with which is doped or which is added trivalent impurity is called as a p-type semiconductor. Now trivalent means obviously 3 electrons in the valence band or outer band of the impurity atom. So typical examples of trivalent impurities are gallium with atomic number 31 and indium with atomic number 49. So let's see the bond formation in this p-type semiconductors doped with trivalent impurity. Now here similarly the gallium trivalent impurity positions itself in between 4 neighboring germanium semiconductor atoms. Now we know that gallium has 3 electrons in its outer valence band. Now it exhausts 3 of its valence electrons to form 3 covalent bonds with 3 neighboring germanium atoms, with 1 electron contribution from each of the germanium atom and 1 electron each from the gallium, 1 electron from gallium. So 3 covalent bonds are formed where gallium exhausts 3 of its valence electrons, and this bond with the 4th neighboring germanium atom is formed with 1 electron contribution from germanium only. Gallium does not contribute an electron. So there is a vacant spot or vacant electronic spot in this covalent bond. Now this deficiency of electron or absence of electron in this covalent bond is called as hole. So the hole is nothing but the absence or deficiency of an electron in the covalent bond between the trivalent impurity and the semiconductor atom. Now these holes act as powerful attraction sites for neighboring electrons. Neighboring electrons rush to fill this spot and thus create another vacancy or hole in their original site or original location. So this hole, as it attracts electrons from neighboring places, acts as a charge carrier. Now this hole acts as the majority charge carrier in this case. So as the hole or the deficiency of electron creates a net positive charge, so that's why these semiconductors, this type of extrinsic semiconductor is called as p-type semiconductor or positive type semiconductor. Now here gallium accepts electrons from neighboring atoms, so that's why it is called as an acceptor impurity. So here we have discussed with you some of the basic introductory concepts about semiconductors. Now starting from the classification, the bond formation and various types of semiconductors, introductory concepts about the various classifications. So I hope you like this video, and please subscribe my channel for more such videos related to electronics engineering, and thank you very much. Have a great day. Thank you.